So, welcome everybody. This is actually the second event of this series with Stockholm AI that we're doing. It's called Slice of AI. So the goal of this series is focusing on some more academic part of AI, if you want, but then also trying on application and also to industry, but in general, also to society in some sense. We're doing this with the support of Silo AI that is giving, and Combient, which are giving us both this office and some refreshment later on. Today, the topic is going to be satellite imaging and remote sensing, and Saroosh is going to be presenter. So satellite imaging, we'll soon discover what it is and how deep learning can help us. This is kind of an important field and an application of AI. Because differently from many others, satellite imaging could actually help us when it comes to climate change and agriculture, and also to monitor humanitarian crises, for example. So now I leave the stage to Saroosh, and enjoy.
Hi, everyone. So I'm Saroosh. I'm an AI scientist at Silo AI and colleague of Pier, and I'm going to be talking about satellite imaging and deep learning in the context of satellite imaging. So we're basically going to be focusing on this paper here, which is one of the first applications of transformers for satellite imaging. In the process, we'll have to cover one of the first papers that applied transformers to images, which was back in 2021, and then a few more on the way, which was then transformers for videos in late 2021. So why do we care about this? First of all, there's been an exponential increase in satellite data recently, as you can see. So we are acquiring more and more images, Earth observation images, and it's becoming more and more vital to be able to do some sort of almost real-time analysis of the data to be able to take action on relevant domains. And they're fairly quick in acquiring a succession of images for a particular location, which allows us to be able to monitor these locations in almost real time. And also there's tend to be a constellation of satellites from which you can aggregate the data for the same location and increase your inference for your particular domain. All the satellites tend to have various different kinds of sensors. They can be radar, synthetic aperture radar sensors, which basically solves the problem of going through cloud cover and so on. And then they tend to be the mostly used are the visible light and near infrared sensors, which allows us to see human activity on the ground, more or less. And the paper basically that we focus on is on the visible light and near infrared. That's what it uses. For the use case of land cover recognition and monitoring, it's already in place, the early warning systems for potential deforestation. And what it does basically is reduces the need for on-site inspection. This image comes from somewhere in Brazil, Amazon, and within 1 month, this amount of change had been tracked by Planet Labs. And then, so they were able to take action to be able to reverse this. On the link there, one is able to see how the change has progressed over time. So they more or less reversed the deforestation in this patch. Other use cases are forest health monitoring, because vegetations tend to reflect differently for healthy vegetation versus non-healthy. So one is able to see also the water content. So that helps one monitor the forest health. And then one can also do tree or crop type classification also. The difference here is that one needs to be able to have temporal patterns of growth to be able to detect which particular kind of species of crop or tree it is. So from static satellite images, one is already in the domain of time series of satellite images. So here is an example of applying semantic segmentation to a patch of field, and then we are able to detect what kind of crop it is. So these are the classes, the kinds of classes that are used in the paper also that we are going to look at. In the paper itself, they don't measure what classes are there, but they are mentioned in the supplementary. So before transformers, what has been happening is that these are based on extracted features from, for example, what's known as the normalized difference vegetation index, which is basically aggregate of infrared and near infrared bands. So this is able to give you a measure of how healthy the vegetation is. But again, this is based on extracted features, which you have to do before passing the data to your neural network. But okay, so what happened after 2019 was basically the transformers have been taking over. So any kind of data you want to be able to pass it to a transformer to make inference. And there is good reason for that, because transformers tend to be the most generalized kind of neural networks that they can be. They don't have any inductive biases. I'm going to talk a little bit more about how convolution CNNs have inductive biases. But so yeah, so the effort has been to, after NLP, to be able to apply transformers to as many domains as possible, or as many kind of data. So this happened in 2018, and then, as I said, it was 2021 when transformers were first applied to images, which is a fairly long time in the time frame of deep learning. The problem here is that attention grows quadratically with the number of tokens. So one cannot apply it directly to pixels. So this is the main problem, because there's just too much data for a transformer to be able to process efficiently. So how they solved this in 2021 was a paper by people in Google, actually. So what they do is, instead of dealing with pixels, they divide the image into patches, and then they process the patches to be able to pass them to the transformer. So what they do is, they unroll the patches into a sequence, they embed and flatten the patches, and then they add the positional encoding on top. So this 1, 2, 3, 4, 5 is basically denotes a positional encoding. It's a learnable embedding also. And then there's this is the first trick they use to be able to use it with the images. That is, they add what they call a class token. It's a randomly initialized token, which is learned through the network. So they add this, and then this becomes the feature map after this, which is what they pass to the transformer encoder. And then they do the classification. So this was basically the one thing that was allowed them to be able to process image data through transformers. I had some notes here, actually. I'll skip them. So what is the difference between vision transformers and convolutional neural networks here? Well, the one thing is that in convolutional neural network, the receptive field grows with the depth of the layers. But for transformers or vision transformers, particularly because attention is always global, it's global in every layer. So the transformer knows everything about everything at each layer, which is not the case for convolutional neural networks, which is the reason why they've been favorable for tasks with limited data. I mean convolutional neural networks, because of this, their inductive biases, which is translational invariance. So they are particularly useful when you have scarce data, or yeah, exactly. But when we go into the domain of large data, and transformers are able to process them much more efficiently, they don't have the bottleneck that convolutional neural networks have. Large-scale training, of course, trumps inductive biases in the end. So if you're in the, do you have a question?
Transformers. What does it happen? Like, for example, I understand the process, and like what does in that process, but when it comes to transform,
yeah. You mean the attention mechanism? Yeah, I decided to not make any slides about that. But what? Okay. I'm just thinking where to begin. So basically, it's in a way you can think about it's calculating similarity between each pair of token, and then it learns how what the weights are for that, and then applies it at inference time in the decoder. So, do you want to jump in here to try to explain it? So that would be a one-liner. But of course, like what I would like to show is like key query value and how that works. But I don't have a slide ready for that. I'm sorry. But I can point you to something after. Yeah. Yeah. Okay. So then that's the vision transformer. But then now, how do we deal with time series data, which is basically videos? And then there was this paper, which came soon after the vision transformer. And what they basically do is they present different ways of applying the encoder to the different dimensions, spatial and temporal. And then they evaluate the merits of each of it also. But then the point being that when you have the temporal dimension also, it's also another dimension that the attention mechanism has to account for. And either one can apply attention completely to the spatial dimensions and then go to the temporal part, which is a factorized encoder. So you're applying attention to each dimension separately, or you do it one by one, spatial temporal in one layer, and then again spatial temporal in the other layer. And then we come to the paper that is the main theme of this presentation, which is that how they do is basically apply the same kind of factorization, but they apply the temporal and then spatial, and then they motivate why they do it. It's because of certain specialities of satellite imaging data, which is different from natural images, or yeah. So where they apply the temporal encoder. So so on the x-axis here, imagine that's the time axis. So this is the patches one image at time t equals 1, t equals 2, and t equals n, let's say. So then, yeah, and then each of the patch here is presented separately in a different color. It's important when you, in the next slides. So they reshape it as was done in the vision transformer paper. There's nothing different here, except that there's the increase in the temporal dimensions. And then they add the positional encoding to each patch. As you see, this patch and the positional encodings are referring to this patch for all times. The green shade is used to indicate the time dimension. And then this patch is shown here, and then this patch is shown here, basically. So we apply the positional embedding here, and then, right. Yes, so it's again to show that each of these patches are represented in each of these blocks separately. Okay, and then we add the class token as in the vision transformer. But here there are, let's say, k class tokens for each time acquisition point. So this is time 0, 1, 2, and then there are class tokens for each of these time points. So each of the block of patch embeddings gets their k set of class tokens. And I went too fast, sorry. Which is then passed on to the transformer. And then after lost my pointer, after the transformer, all the patch tokens are discarded except the class tokens for each patch. So that's basically what they're doing. After that, this is the temporal encoder. And after that, they pass this to the spatial encoder, which is like taking all the class tokens for each patch, adding the same process, which was done for the vanilla vision transformer, position tokens for each patch, class tokens for each patch, and then passing it out to the transformer. And the output of that, yes, output of that is then, for example, passed on to the segmentation head to be able to segment what the different patches have inside, which is then reassembled. So basically, this is the difference from the basic vision transformer in that it's extended in the temporal dimension. So you've added another transformer encoder for space and time.
Question.
Yes.
Class tokens in the two encoders, same set, same set of classes in the two Canadian.
No, it's
they depicted with red and blue here, but
it's the same set.
it's the same set.
Yeah.
So it just updates the class.
Yeah, exactly. Yeah. Yeah. So yeah.
Can you elaborate spatial encoder one more time? I didn't follow what you said.
So it's actually exactly the same stuff that's happening, except it's not applied to the raw patches. It's applied to the output of the temporal encoder. But the process is exactly the same. For you then apply the positional embedding and the class token, and I pass it again to the transform. But it's already transformed at this stage. That's basically the thing.
So for the embeddings, do we use any specific type of embeddings, or is just converting the patches to number?
It's just that, and then it's learned. They're learned. Yeah. And then that's I don't know. Maybe we don't want to get into it. Why should one have learned embeddings? Why not just hardcode them? But I mean, that's the point of deep learning, I guess. Anyway, yeah, so here we are, and we have segmentation, semantic segmentation at the end of it. Here are some of the results which were not actually in the paper, but they're in the supplementary. And to compare to all the other, like compared to the state of the art up until this point, which are basically convolutional based or LSTMs, the TS-WIT tends to perform much better. What's been shown here, if the cross pixels are the ones that were segmented or classified incorrectly. So this is the R guy, and it tends to be doing pretty good if you are to qualitatively judge it by the number of crosses here. Other than that, we can look at perhaps, so one of the more interesting results are the ablation studies here, where they compare the factorization order, whether it's better to factorize first spatially and then temporally, and vice versa. And here it shows that they have quite a gain in performance or accuracy if they do temporal and spatial encoding, as it was demonstrated. And then they try to justify it in a way. Well, what they're saying is that one of the reasons to be able to do that is that the information is not changing as much spatially in satellite image data because not as much as natural images where you have moving objects and so on. So it doesn't change as much. So it's better to condense the information that's present in the temporal domain first and learn from that, and then pass it on to the spatial encoder. And for their case of it looks much better. Then they also compare if it matters for the number of class tokens they add, and for the temporal encoder, we saw that they added more tokens for each time acquisition point, and that improves the accuracy also. Then the position encoding static, as we were talking about, or whether it should be based on the temporal encoding, the temporal acquisition point. Date lookup, it's how they refer to it is actually, if you look in the code, it's not that clear. What they actually end up doing is basically, just having temporal encoding or spatial encoding for each time point, and then adding the particular embedding for that point to the patch instead of having a lookup table. And then the patch size also, and that's quite intuitive. The bigger the patch size, the less information, or
Is that in pixels?
so exactly no, patch size isn't pixels. Patch size is how you've cut up the image, basically.
Okay.
Yeah. So it's better to have smaller and many patches instead of big and fewer patches, because that's basically ultimately the input to your net.
What does it refer to?
Oh yeah, no, that refers to pixels. Sorry, yes. Yeah. Sorry, yeah. It is pixels. Yeah, smaller is better. Yes. Yeah. So this is the. Yeah. So to understand what kind of data they have, it's fairly low res. Let's see. The pastis is mentioned here. Where is the resolution? So this is 128 by 128, but the one for Germany is much smaller. So this is the highest resolution they have, which is pretty low also. And the difference with it's many more bands than just regular RGB images. So that's the difference with the satellite image data. So these were interesting results, which sort of motivate their choice of design by demonstration, but it's not motivated theoretically as much or as usual. And then this table compares how the performance is compared to state of the art. Tends to be good for, there is an increase over semantic segmentation metrics, and then the classification also. Whether it's great or not, I mean, I don't know, but there is an improvement. And then the fact that transformers don't have as much or any inductive biases baked in, as we go into the domain of large data, it becomes more and more easier to apply them, essentially. So that's basically what I was gonna say. And now we can take more questions if there are. Yes?
The training bit. Supervised only?
It's supervised, yes. Yes. Yeah. And then they have much more information about their training schedule and the optimizer that they've used, which you can find on this in the supplementary.
I can ask a question.
Yeah.
Real world data, there will be other changes in light across the thing.
Yeah.
I think this will change which order is better.
Which order?
How do you think that seasonality would be captured?
So
the same type of thing. If you want to do it like
yeah. Well, okay, there are a few points there. For one, for this particular case, for example, crop classification or species classification, you actually do need seasonal variation. So the network learns by how each particular species changes over time, which is different for each species. So in that sense, seasonality is important. About the fact that the conditions would change, for example, cloud cover, there could be cloud cover and so on. I mean, that's basically disregarded then. And also the acquisition time, the revisit time tends to change. And that's the point when they construct the temporal encoder, it's based on the actual acquisition time, which means that some of the images have been discarded. It's not equally spaced in time. So there is some pre-filtering.
Yeah, because these satellites follow some synchronous orbit, so they will have roughly the same time of day.
Okay.
Oh, yeah, time.
Okay, so every image of the same patch, or you know, for it's gonna sometimes the day when it's
yeah, so I mean, for the same place, it's going to be roughly the same.
Okay.
Day.
Yeah. Thank you. Yes.
On the first slide, they showed about the satellite images. I didn't quite understand what did the model do to the images and how it got almost like what happened. Like
the first slide.
Yeah.
Share this. Sorry, which slide do you mean? This one. Yeah, so this is basically showing that within one day they're able to see that there is a difference. There's no modeling going on here unless they have installed a monitoring system. So this was just an example to show that there is enough data that can show you a change over a month. So this is just a demonstration of how satellite image data looks like. But I'm not referring to any model here. Yeah.
Example of an application.
Yeah, exactly, an application. It's basically, yeah. So if you had monitoring on top of this data, you would get an alert maybe that there's been too much of a change and you should take some action and go have a look what's going on.
One of the objectives in the paper is segmentation.
Yeah. Yeah.
What data did you use? Was it open access?
What data does the paper use? They mention it in the paper. It's pastis, and then I don't know which, if it's derived from Sentinel or something. I'm not sure. And then some other data set, but it's referred to in the paper. Yeah. Yeah.
So when you go from these patches to the vectors,
Yes.
is that basically putting the pixels in a vector, or how
Yes.
is that projection?
Now I'm not so sure. Yeah, so it's. Yeah, do you want to say something, Pierre? How is the embedding done from the patch? Yeah, they didn't quite mention in the paper how they've done it. And I didn't look that in the code. Yeah. No, go on.
One day.
Ah, well, yeah, okay. Yeah, it's one there, yeah. Yeah. No, sure. Yeah, there are more. Ah, okay. Do you want to go? Okay, after. Yes, Louisa.
Is there like any other use cases that you can use the same technique, like very soon?
Apart from
Like other patterns on Earth that you can like detect that this like using?
I mean, any kind of semantic segmentation, basically.
Yeah, but do you know any like you?
So, I mean, these are two different use cases. For example, for forest health monitoring would be one.
Okay.
Crop classification would be another.
But could it be used like in the future when it's more detailed, like to find the criminals wherever they are on Earth or something like this?
I mean, I think there are. They do try to classify, for example, vehicles versus buildings. That's quite easy to do. And I don't know, maybe criminals tend to go in particular kind of buildings. So yeah, I guess so. I'm sorry. Yeah. Okay.
Even like wildfires.
Yeah, and
That
wildfires.
could be,
So climate change.
how big they are, like,
Yeah, there are implementations of wildfire monitoring already.
oh yeah, like burn 2,000. And this can also see like you don't need to see.
There's people in Spain that are using it to try to figure out if there are Roman structures.
Oh.
I don't know.
Yeah. That must be like very dirty. Yes.
One simple question: do you do any pre-processing of data, this downscaling?
No, the data set that they base the training on, it has some pre-processing already in the sense that images with too much cloud cover, they're already pre-discarded. But the paper itself doesn't do any pre-processing. Yeah. Yeah. Yes. I mean, of course, they do the embedding and so on. That's all. Okay. Yeah, there was someone else. No, yeah.
Question, actually. Back to the use case. I'm wondering, so they basically speak about English, but paper, I know to get a sense for how much are the results tied to that application and specific features of that application, and how much of this generalized.
Yeah, I mean, now I'll have to guess here. I don't know. I think what I think is that there's higher variability in data for crops than there would be in trees, for example. Also, crops have a shorter growth cycle. So within one season, you would have the full growth cycles. And the growth cycle is particularly important for crop classification. For trees, they tend, for forests, I mean, they tend to be fairly static. And they're not changing that much. So in that sense, that would be a bit more difficult, is my guess. On the other hand, the use cases are exactly not the same for forests versus crops. For crops, why they want to do it, for example, EU has a regulation now that they try to compensate farmers which are growing more sustainably, which means having a more diverse crop cover on the field, which can be helpful in this. For forests, it would mostly be like deforestation, but then also like in Sweden, for example, where you have a lot of forests which are used for paper and so on, maybe it would be helpful to monitor when you have started replenishing them, how that's going. Is it following, is it on track or not? Yeah, so I don't know if semantic segmentation would be useful in that sense.
To say that the fact that crops change times a year is an important feature.
Yeah, what they found was that the growth cycle, to have captured the whole growth cycle for all the crops, helped in classifying them, because they change differently, reflectance changes for each crop differently. Some grow quicker, some grow slower. So that helped. Yeah. It is difficult to do for a first. Yes.
Do they mention anywhere in the study how sensitive it is to temporal versus spatial?
Yeah, I think I showed the, oh my God, now I'm so scared of losing my tabs again. Right, now they're gone again. Oh, here, yes, wonderful.
Crops are pretty stationary. Something that's moving.
Yeah, exactly. So that's what the justification they give also. Crops are fairly stationary.
Yeah.
And so they're not, the patches are not moving boundaries as quickly, which is why they do the temporal factorization first. Yeah.
And so the question was, do they know how sensitive it is to varying data?
Yeah, so exactly. So if they did spatial first and then temporal, this is their mean intersection over union. For the crops, yes, crop segmentation. And then if they do temporal versus spatial, it increases by this much. So there's quite a gain there.
Yeah. So these numbers would likely look very different if it was if the motive was something else.
Yeah, exactly. So that's the design choice that would be informed by the data and the use case. Yes. Yeah. Yes.
The minimum size of the past is important, and the reason is criminal activity. Just earlier, you have people growing, I don't know, hash stuff within official growing fields. But these tend to be small. To be able to detect this.
I mean, judging from the resolution here, if it's very small area, I think it would be very difficult. It has to have some enough. I think, yeah, the easiest thing would be to say it has to have enough.
Acre or, I don't know, 10 acre?
Let's see. So, for example, this is this, and then yeah, but then when they move it to pixels, 24 by 24. So if we do the math, what do we get? 24. So it's, I guess, 5 kilometer, right? Here. It would be 5 kilometer here. But I'm not saying if that's the theoretical limit. But judging from this, given that they have this large an area and then they're going by this size of pixels, what they're able to show at least is for around 25 kilometer. If I'm doing the math right. If I'm not, someone should call out. But no one is doing the math here.
Samples cover 240.
What? Sorry?
In same samples, those individual image samples cover.
Oh, yeah, it does. Yeah, exactly. So I was right. The math was right there.
So it's a big size here.
So the patch size here, that was your question, that was 25, yeah, around 240 by 240 meters square. And then the pixels is, for each patch, there's 24 by 24 pixels. Fairly low res. And fairly big patch. For pastis, 24 by 24 patches. I think it's the same. But I don't know the theoretical lower limit. But it also depends on each, of course. I mean, satellites have different resolutions. Some satellites are much lower orbit, and they have a higher resolution. So, yeah, exactly. So I have seen satellite images which are fairly close and are able to discriminate between buildings versus cars, for example. So they do exist, and I guess they would be good enough for this kind of work. Alex?
This is maybe in the beginning you mentioned that there can be multiple types of images, same thing in the sense that you monitor the infrared spectrum of it, but also side of that or okay.
Yeah.
So is this architecture based on like two-dimensional image or
No.
like a tensor image?
Yeah, it's a tensor input. So yeah, exactly. So there are 10 bands.
Okay.
Compared to RGB, which would be 3 channels, and 10 to 13, for example. Yeah. Yeah. So most of the satellites tend to have different kind of sensors. Both like they capture optical, and then some of them have radar also to be able to see through cloud cover and so on. And then they have all that data available for all their acquisitions. Yep.
Yeah, so in the where it says the interactions between cluster access and spatial,
Yeah.
does that mean that the impact of the spatial cluster is really as relevant as the temporal?
So this is something that we were discussing, Pierre and I. And I now can't recall what conclusion we came to. So what was the deal with the interactions of tokens? All right. Yeah. Yeah.
And then you spend them every time.
Mm.
The first case you can have interaction.
Yeah.
Then you see this car, the button and one key textbook, and the that's going to be some addition lane. So we're playing speculation. Say, okay, it's time already. So, third party strike side. That's it.
Yes.
I guess in the sense of
Sorry.
the crop type detection, the crop is still stationary. So
Yeah, exactly. It's not moving. Yeah. They do mention that in the paper. Yeah.
As far as I'm concerned, that CNN was the state of part. But part of the comparison is made on CNN, especially this kind of like from
Yeah. Yeah, this is the comparison, basically. So, for example, this is a CNN. And what I was saying applies here is that CNNs do tend to do better in data scarce cases. If you have less data, they will always outperform transformers. But in the domain of large, if you have large enough data, transformers will always outperform CNNs. And that they saw already for the vision transformer when it was shown in 2021.
So it has to do with
Yeah, exactly. And the inductive biases that CNNs have, which helps in data scarce environment. Yes, Louisa.
Is it how fast is it like it scans like the whole Earth and it's like immediately you see all these spots, or it's like you select this special area and you do like.
I've never driven a satellite, so I'm not quite sure. But I think how it works is, I think you select a point, and then it either does a full pass and returns at the same time.
And then it's going to be like live, the changes happening.
Some satellites are like that. I think the satellites the military uses, they are, of course, they're changed quickly. Some are like what's called stationary satellites, which are just staying within the same orbit as. But it depends on satellite. There's so many, and there's quite a lot of variety. Yeah. But it like, for example, oh my God. Here, no, here, here you can see that within 12 to 48 hours, they can acquire data for a whole globe if you have like a constellation of satellites. And then the low Earth orbit, they do a pass around Earth between 90 minutes and 2 hours. So they can move that fast. So they can go around in just 2 hours. Yeah.
Commercial systems built on top of that.
I think there are quite a few. I guess the Planet Labs, they have.
No, I'm not talking about satellites. Sorry.
Oh.
The core of your presentation.
I mean, if there are commercial, we don't know what it's based on, but there are systems that do semantic segmentation and like crop classification in place. That's been done. There are a lot of the explosion in satellites has mostly been from the commercial sector. So a lot of companies sell satellite data for these kind of use cases. And then downstream, I'm sure there are a lot of applications or systems built on top of them. I don't know particularly for Sweden, though. What's out there?
if we look out instead of in, as some of these techniques being used for scientific discovery.
I mean, astronomical.
Yeah, new planets.
No.
It makes sense to look up.
Yeah.
There are telescopes out there.
Yeah, I mean, Hubble and Weber, they're doing that part. Sorry?
I mean, the data of building it.
But also you want to have it like quite fast reactions, right? And it's like billions of light years away. So
See if there's
Maybe someone has tried, but
okay.
you do discover.
So I don't think these have been used, but the way it actually works is again, right? And the method that's done is for deviation. So it's morally a subtraction of images where you see a change from an average. And if you're thinking about things that are moving, you find these things that rip up and you join them. That's basically the method that is used to find planets or asteroids that are closer.
but I suppose those are not based on low orbit satellites.
No, they are basically based mostly on ground-based telescopes
Yeah.
or telescopes of satellites.
Yeah, I guess like if you,
So
yeah,
yeah,
I guess, yeah, that makes sense.
it's actually what is interesting is that you also have objects that are static and change,
Mhm.
and it's only the temporal thing that's applied that the image reveals. And the planets, as Alex was suggesting, you combine these two, and so it's interesting to think about whether these kinds of things can also be applied.
Yeah. Yeah, first I was thinking it doesn't make sense to use low orbit satellites, but then telescopes are on ground. So yeah, exactly. So I guess if there is a possibility, but these are so low resolution. That's basically maybe the killer.
Transformer has that large data.
Yeah.
So that's just a question.
Hmm.
I think the data is much larger.
Yeah, it's okay.
Most of it is.
All right. How are you feeling? Good. Great. Thank you, everyone. Thank you.